good morning, good evening, or good night, whoever's watching this video. This is mostly for my professor, but if anyone else stumbles upon this channel, welcome. I hope the fan is not too windy. It's really hot today. And this is part of my data structure assignment to explain most of the problems and their solutions in LeetCode. Now, I did need some help, obviously. I had some good time and some back and forth talking with ChatGPT and trying to find a reasoning. Excuse me for 1 second. Apologies for that interruption. My mom just walked in on me. Anyway, so the part of the assignment is to explain each and every little part of the code, or explain the processing. Well, I talked to ChatGPT. I went back and forth. I consulted ideas and I consulted ways to complete these codes, and these are the best things that I could come up with. So for the two-sum, the very first one I decided to take because it's an easy one. Given an array of integers, nums, and an integer target, return indices of the two numbers such that they add up to the target. You may assume that each input would have exactly one solution, and you may not use the exact same element twice. You can return to the answer in any order, and here are the examples. So right here, so the problem asks us to find two numbers in an array that add up to a target value and return their indices. So instead of checking every possible pair, we use a dictionary called map to store numbers, as already seen in the indices. So, here we have the integer map, or a dictionary called map. Then down here we loop through the array one time, checking each number only once. Then for each number we calculate. Let me see here. For each number we calculate, where we need to reach as a target. This value is called the complement. This is the thing we're trying to reach. So instead of searching for pairs, we need to ask ourselves, or we need to, seek out and look, what numbers do we need to complete the sum? And then we go down here, and it moves to the if inside the for loop. We check for the complement that has already been seen. If it exists in the dictionary, that means we found the correct pair. So we immediately return both indices right here, boom. And if the complement is not found, then we store the current number and its index in the dictionary, so it can be used later if needed. And the return here is just a fallback, so if it doesn't work, oops, that was one of my friends playing Marvel Rivals. But yeah, this line down here is a fallback. Pretty much that. What I said. So man, he's playing a lot. I can't cut that out of the video, so I'm gonna have to hurry and do bits and bits for every piece of code. So let me pause here. 3 minutes already, geez. Hello, welcome back. So for this, I've decided to use a script and read from a script because it would be better that way, and also explain my reasoning. Because if I started explaining my way and started to think of things my way and concentrate on these things, I get lost pretty easily. So I'll be reading from a script. I didn't want to try to sound too robotic, but since the first exercise took me already 3 minutes to explain, I will just fall back on the script. So for this problem, it asks us to remove duplicates from a sorted array in place and return the number of unique elements. The first thing we do is handle the edge case where the array is empty. If it is 1, immediately return 0, which is this right here. We then create a variable called k, which represents the position where the next unique value should be placed. I started at 1 because the first element is always considered unique. Or, my bad. Yeah. We started at 1. Man, the script sucks. Anyway, next we loop through the array starting from index 1, comparing each element to the previous unique element. Since the array is sorted, duplicates will always be the next to each other. So I check if the current number is different from the last unique number I stored. If it is different, I move that value forward to the array position k, right here, and then they increment k. This effectively builds the list of unique values in the beginning of the array. And then we return k if, we exit the for loop. This solution uses a two-pointer approach. One pointer scans through the array, and the other tracks where the place Where to place the next unique value, because the array is already sorted, duplicates appear consecutively, which allows us to solve the problem in a single pass with O(n) time and O1 with extra space. I'll pause here for the next one. Alright, here we go in the next exercise. My mistake, I'm just like returning from eating a delicious meal. I had my dinner, anyway. So this one, 6, 7, given the two binary strings A and B, return their sum as a binary string. This problem asks us to add two binary strings and return the result as another binary string. Since we are working with strings instead of numbers, we simulate binary addition manually. We start from the end of both strings because binary addition works from right to left, just like normal addition. We also use a variable called carry to store overflow when a sum exceeds 1, which is this right here. We use a string builder to efficiently build the result as we compute each binary digit. Use this line of code right here. We loop as long as there are still digits left in either string or there is a remaining carry. This ensures we process all values completely. This is this loop right here, or while. For each step, we start by adding the current carry to the sum. We then add the current digit from string A. If there are still digits remaining, we subtract 0 to convert the character into an integer. We do the same for string B, adding its current digit into the sum. We compute the binary result. We do sum2 gives the current binary digit, sum divided by 2 gives the new carry, and we append the result digit to our string builder, which is this down here. Right here. No, this is this right here, my bad. Then down here, we built this result from right to left. We reverse it before returning the final binary string. This solution simulates binary addition step by step using two pointers and a carry variable. Instead of converting the strings into numbers, we process them digit by digit from right to left. This allows us to handle very large inputs efficiently with a time complexity of 0n. Stop there. So continuing on, we have the square root here, or exercise 6-9, because I felt like choosing the funniest numbers possible. Or I guess the ones that I saw benefited me the most. Anyway, this problem asks us to find the square root of a non-negative integer and return the value rounded down. We're not allowed to use built-in square root functions, so we must compute it manually. We first handle edge cases where the input is 0 or 1, since their square roots are the same as the number itself. This up here. We then set up a binary search frame from 0 to x. We also keep a variable called answer, which will store the best valid square root found so far. We use long instead of int to avoid overflow in multiplying numbers, because long is more capable of holding longer numbers than int. We then use a binary search loop to efficiently narrow down the possible square root. And at each step, we calculate the middle value and square it to see how close it is to x, which is this equation right here. If the square equals x exactly, we immediately return the result because we found the exact square root. If the square is less than x, which is this unfavorable outcome down here, which is the else if, it means we are still below the correct square root. We store this value as a possible answer and move the search to the right side to try larger values. If the square is greater than x, we move to the left side to try find smaller values. Finally, we return the last stored value, which is down here, which is the return. We always have this for every piece of code, usually. Where we return the answer that we are given when one of these is completed, or one of these is finished. This solution uses binary search to efficiently find the square root without using built-in math functions. Instead of checking every number one by one, we repeatedly divide the search space in half. This makes the solution much faster with a time complexity of logarithmic n. I'll continue to the next one. So, this is the shortest one out of all of the 5 easy ones given. So this problem asks us to determine whether two binary trees are the same. Two trees are considered the same if they have identical structure and the same values in every corresponding node. As you can see here, these are the examples given. These are some of the things that we learned during class, as you can see over here, we start by checking on this if both nodes are full. If they are both empty at the same time, that means this part of the tree matches, so we return true. Next, we check if only one of the nodes is full null. If one tree has a node where the others do not, then the structures are different, so we return false right here. And then we compare the values of the current nodes. If the values are different, the trees are not the same, so we return false immediately. And finally, if the current nodes match, we recursively check both the left and right subtrees. We only return true if both subtrees are also identical. This solution right here uses recursion to compare two binary tree node by node. At each step, we check structure values and then recursively verify both left and right subtrees. If all conditions matches, the trees are considered identical. This approach runs in n times since every node is visited at least once. So this is one of the medium problems. This is the divide two integers. So this problem right here asks us to divide two integers without using multiplication, division, or modulus operators. Let's also truncate the result towards 0. Logically, we first handle a special edge case. When dividing the minimum integer value by -1, the result would overflow the 32-bit integer range, so we directly return the maximum integer value. This is that if right here. Scroll a little bit more down. Next, we determine the sign of the result. We use XOR operation to check if exactly one of the numbers is negative. If so, the result will be negative. There's here the bool negative. Right here. We then convert both numbers to positive values using long to avoid overflow issues. We also initialize a result variable to store the quotient, which is this part right here. After that, we create a temporary value for the divisor, there we go, and a counter called multiple, which tracks how many times we are subtracting, which is this equation right here. Inside the while loop, then we have another while loop. Instead of subtracting the divisor one step at a time, we double it using bit shifting. This allows us to subtract large chunks quickly, making the algorithm much more efficient, which is this while loop right here. We subtract the largest valid chunk from the dividend and add the corresponding multiple to the result. Finally, we apply the correct sign to the result and return the final quotient. This simulation, all of this right here, simulates division by repeatedly subtracting large power of two multiples of the divisor instead of subtracting one at a time. By using bit shifting, we significantly improve efficiency. The time complexity is O log n, which is, how would you call it? It is optimal, making it much faster than a naive subtraction approach. That's what I believe would be the best approach, because from what I saw, from what I looked into, all the other approaches are slower, and this is one of the faster ones. So there you go. Finally, we conclude this video with the other medium, unless I decide to do the hard, which is, or one hard leak code thing. I might do it, but it is hard and it is only a bonus, so. But anyway, another binary search tree, a unique binary search tree. I chose this one because I thought it would be simple. It was sort of simple, and because it's something that I'm already versed in and I have studied for a bit while in this class. So, as we can see here, this problem asks us to find how many structurally unique binary search trees we can build using values from 1 to n. We use dynamic programming to solve this efficiently. First, we create an array called dp, right up here, where each index represents the number of unique BSTs possible with that many nodes. We initialize the base cases. An empty tree counts as one valid structure, and a tree with one node also has only one possible structure. We then build solutions from smaller values up to n using a bottom-up approach, which is this right here, this for loop right here. So at the for loop, there's another loop. For each number of nodes, we try every possible value as the root of the tree. Each choice of root divides the remaining nodes into a left and right subtree. We then, down here, go inside the other for loop, to calculate how many nodes would go into the left subtree and how many would go into the right subtree based on the chosen root. You then come down here to the total number of trees for a given root is the number of left subtree combinations multiplied by the number of right subtree combinations. We add all possibilities together for each root choice. Finally, we return the results stored at DPN, which represents the total number of unique BSTs that can be formed with the end nodes, which is BSTs is unique binary search trees, by the way, BSTs. I love acronyms. Anyway, the solution to this problem uses dynamic programming based on the idea that each number can act as a root and split the problem into left and right subtrees. By combining all possible subtree configurations, we compute the total number of unique binary search trees. This follows the Catalan number pattern and runs in O(n) square time. Square 2. O(n) 2 time. Or O(n) to the power of 2. Should be that, yeah. Anyway, that should be it concluding. If I continue and make a section for the hard, then it will be after this. If not, I gave up. Well, I didn't give up. I didn't do the bonus hard one. But I do apologize if I sounded quite robotic or if I followed a very determined script. I wanted to make this video as short as possible, and having to explain these codes and the solutions and the problems and the reasonings is, hard if I say it from memory. If I follow a script, I feel like it is way better and more concise and more appropriate. So I'm going to leave it there for now. I hope whoever's watching or whoever has watched had a great time watching, especially you, Professor. Oh, excuse me. I should cut that out of the video, but I don't know how to edit the video properly, so my mistake. Anyway, I'm so sorry. I'll leave the video up in there. I love your class, Professor, and I hope you're having a wonderful day, night, or evening, wherever or whatever you're doing. Love you, Professor, and yeah. That's going to conclude it for this video. Thank you, whoever's watching, for watching, and I'll leave it there. If I do make another hard one, I'll add it to the end, but we'll see what happens.